Hi everyone. Today I'll be talking about inverse functions, which is one of your topics in the syllabus for Year 12 Maths Extension 1. So we've spoken a little bit about inverse functions before, but today what I want to concentrate on is how to find the exact values involving inverse functions, and then later on using inverse functions in equations as well. Okay, so let's start off with having a look at how we would go about finding the exact values when we have inverse functions. And how we do that is by using the method of substitutions. So you can see here we have sine of inverse sine A. And how we find out what A equals to, or what the exact value of that equals to, is we can let that equal to x. Can you see that? And once we've let it equal to x, this is a really important step. We can change the input of the sine to become the output here. Can you see how the input of inverse sine A becomes the output over here? Yeah? And now the output of this, which is x, becomes the input. And you can notice that whereby we used to have sine here, we have to change that to inverse sine. So a good way to think about this is if we consider sine of 30 degrees, yeah? And the exact value of this is 1 on 2. Now, if we switch the input of this to the other side, and make the output into the input, then this becomes inverse sine, doesn't it? Because the inverse sine of half equals to 30 degrees. So can you see how when we switch the input to the output, we must always switch the sine into inverse sine here. And then the reverse would have to occur, wouldn't it? So for example here, if we had inverse sine half equals to 30 degrees, and we switched around these two, then we have to change from inverse sine back into sine. Does that make sense? So just remember, whenever you're switching your input and outputs, we must also change the sign. So from here, you can see that we have inverse sine x equals to inverse sine A. Now, because they're both inverse sine, we can conclude that x equals to A. So therefore, from this here, by letting it equal to x, and then switching the input to the output, and then also switching the signs, we have found out that x equals to A. Alright, so the important thing that I want you to learn from this is that we want to make that equal to x, and then what we want to do is switch the input and the outputs, and remember to always switch from sine to inverse sine, or cos to inverse cos, and so on. Okay, let's have a look at some questions now and use what we've just learned here. So starting off with question 1, we want to find the exact value for sine of inverse sine 4 on 5. So the first thing we want to do is let this whole thing equal to x, okay? And now, because we've let it equal to x, remember how we could switch the input to become the output? So that's exactly what we do. We've made this input into the output here, and the x, which was the output, has become the input there, and therefore we must switch this to inverse sine. So now we have inverse sine x equals to inverse sine 4 on 5. So therefore, x equals to 4 on 5. And since we let this equal to x, we can say that therefore the exact value for this here is 4 on 5. Can you see how we got to the answer by using the steps of substitution? Good. Alright, let's move on to question 2 then. So in question 2, we now want to find the exact value for cosine of inverse sine 4 on 5. So you can see here that instead of having sine and inverse sine, this is cosine and inverse sine. So it makes the process slightly different. Alright, let's see how it is slightly different. We want to make, instead of the whole thing equal to x, I only want to make the input equal to x, okay? So when these are different, so if you have tan or cos and sine as we have here, we only want to make the input equal to x. And now, because we switch the input and the output, we switch from inverse sine to sine. So remember how I said it goes both ways? So if we start off with sine, we want to switch to inverse sine. So if we have inverse sine, we switch to sine. So sine x equals to 4 on 5. Now, let's look back to the question. We want to find cosine of this, but we've let that equal to x, haven't we? So essentially now what we want to find is cosine, and this is just x, isn't it? So that means we want to find cos x. And how do we do that? We have to draw a Pythagoras triangle. So this is our right angled triangle. And using the information we have here, that sine x equals to 4 on 5, we know that sine x is opposite on hypotenuse, isn't it? So we have 4 on 5 there. And then by using Pythagoras, so remember we have a squared equals to b squared plus c squared. So we know that 3 squared plus 4 squared equals to 5 squared. We find out that this equals to 3. And so we can say that cos x, which equals to adjacent on hypotenuse, equals to 3 on 5. And cos x is the same as cos of this input. So therefore, the exact value of this is 3 on 5. So can you see how that's slightly different from the question before? The main difference here is we only want to make the input equal to x. And the other difference is that we have to use a Pythagoras triangle to work out what cos x equals to. So remember, we're always going to be working with a triangle in these cases. All right, great. Let's do some more practice together. So in question 3, we want to find the exact value of sine of inverse tan 3 on 7. So you can see the first thing that jumps out to you is that the sine and the tan, they're different, aren't they? Which means that we can't make the whole thing equal to x, but exactly, we just want to make the input equal to x. And now we switch the input and the output, which means that we have to also switch inverse tangent to tangent, yeah? Because whenever we switch these two, we must always switch that. So now we have tangent x equals to 3 on 7. So let's look back to our original question, whereby we want to find sine of this input. But since we've let this input equal to x, essentially what we want to find now is sine x, isn't it? We've made this equal to x. So how are we going to find sine x? Well, we're going to use a Pythagoras triangle here, where we use this information, where we know that tangent x equals to 3 on 7, so that's your opposite on adjacent. And now we use a Pythagoras formula, so 3 squared plus 7 squared equals to the hypotenuse squared. So this equals to square root 58. So once we've found that out, we know now that sine x equals to opposite on hypotenuse, which equals to 3 on square root 58. And now, since x is the input, we can conclude that the exact value for this here equals to 3 on square root 58. Okay, so you can see that this is a very similar process to question 2, isn't it? Where what we want to do when these signs are different is to make only the input equal to x. And then we always have to use the Pythagoras triangle here to work out our exact value. All right, so we're getting familiar to using this process here. But let's keep on practicing so you really remember it. So question 4, let's find the exact value of the tangent of inverse cosine 5 on 13. So this is tangent, this is cosine, so they're different, which means we only want to make the input equal to x. And now we switch the input and the output, which means we want to make the inverse cosine into just cosine there, yeah? And going back to this, we want to find the tangent of x now, because we let this equal to x. And to find that, we use this as the information to draw ourselves a right angled triangle. So we know that cos x is going to be adjacent on hypotenuse. So we know this is 5 and this is 13. And by now we should know that if we have 5 and 13 there, then the other side is going to be 12. So now we'll see for tan x, tan is opposite on adjacent, 12 on 5. So therefore the exact value of this is going to be 12 on 5. So in your exams, it's good to write your final answer as this and not as tan x equals to 12 on 5, because we're not actually trying to find out what tan x equals to. We're using that as a process to work out the exact value of the tangent of inverse cosine 5 on 13. Does that make sense? Whereas if you only write this as your answer, you're showing to the examiner you don't quite understand what we're trying to do in the question. All right, great. Let's have a look at question 5 here. So this is slightly different. We want to find the exact value for inverse sine of 2 on 5 plus inverse cosine 2 on 5. All right, so we have two values here and they're linked by a plus, which means that we actually want to make both of them equal to x and then y. So for the first time, we have two values that we want to let equal to something. So x equals to inverse sine 2 on 5, y equals to inverse cosine 2 on 5. So for both of them, I want to switch the input and the output. So the 2 on 5 here goes to the other side, and the x, the output, becomes the input. And this becomes sine instead of inverse sine. Can you see how I've done that? So this now becomes that sine x equals to 2 on 5 and that cos y equals to 2 on 5. And now this is the important part. We need to put both of these values into the same triangle to answer this question, okay? So the first thing I want you to do is draw a triangle. So just ignore that part first, where we have sine x is going to be opposite on hypotenuse. So that's why we have 2 and 5 there. So where does y have to go for cos y to be 2 on 5? Well, it has to go there, doesn't it? Because you need adjacent on hypotenuse. So can you see how we've made x and y into the same triangle, but it must always satisfy these two? Yeah? Good. So now you can see that in this triangle, x and y has to equal what? It has to equal 90 degrees, doesn't it? Because this is a triangle, 180 degrees. It's right angled, so therefore x and y must equal 90 degrees, which we write as pi on 2 in radians. So therefore, since x equal to this and y equal to that, we can say that the inverse sine of 2 on 5 and inverse cos of 2 on 5 equals to pi on 2. So important points to take away from this question is that when you have these two values, it's okay to let one equal to x and the other one equal to y. And then from here, we need to draw them in the same triangle. And also, it's better to answer these questions in radians. Okay, so let's not answer with 9 degrees, but it's better to answer with pi on 2.